In Chapter 6, which is actually a fairly significant chapter, we're going to start talking about the concept of organic chemistry. And as we're going to see in a minute, organic chemistry primarily deals with compounds made of carbon and a few other elements. Now, the chemistry that we've been dealing with so far with ionics and covalent molecules has predominantly been what's referred to as inorganic chemistry. Specifically, most of the things that are ionic fall into that category. So what's so special about carbon? Well, most of the compounds that we actually deal with in the world are composed of carbon. A lot of the biological substances, your proteins, your carbohydrates, sugars, lipids, all of those things are organic chemistry compounds. In fact, organic compounds are more the common and the others are more the exceptions than the rule. The reason that carbon is so special, first of all, we know where it is. It's in group 4A. And one of the main things that makes this work so well in terms of making a diverse set of molecules is that it forms 4 covalent bonds. And so we can see that in a simple Lewis dot structure of methane, CH4, to more complicated structures once we start introducing other types of elements, double and triple bonds, even loops. But how this all works is that one carbon can bond to another carbon, which can then bond to another and another until they can form all sorts of different structures and connectivities. In organic chemistry, what we're going to see is that connectivity, how the bonds are arranged and what atoms are connected to what other atoms, is actually going to be just as important and sometimes more important than just purely the number of carbons or hydrogens present. So organic chemistry, if we're looking just for a raw definition, this is it. It's the study of carbon-containing compounds and their chemistry, meaning what kind of reactions they undergo. That's what we refer to when we talk about organic chemistry. There's actually 2 and 3 semester courses that deal with nothing but carbon-containing compounds in organic chemistry. We have a 2-semester sequence here at College of DuPage. We can classify organic compounds into 2 basic categories. We can classify them into hydrocarbons, and what hydrocarbons are molecules that only have carbons and hydrogens present. No other no other elements are present in just a pure hydrocarbon. Functionalized hydrocarbons, now we're introducing things like oxygen, sulfur, nitrogen, other elements of that sort to give them different properties than just the basic hydrocarbons. But we're going to look at the hydrocarbons first so that we can get kind of a feel for kind of the base backbone of most of the molecules that we deal with that are then functionalized by the addition of other atoms to give us other properties. Okay. We can also divide these into subfamilies, meaning that each of those groups, the hydrocarbons, for instance, can be divided into alkanes, alkenes, and alkynes. 3 groups that sound very different, don't sound very different, I'm sorry, but are basically different because one has single bonds, another has double, and the last has triple bonds present between the carbons. So there's all sorts of different divisions that we can make, but we're going to stick for now with dividing up the hydrocarbons, and we'll deal with the functional group side, the right side of that last table, later. So the alkanes, which are designated by an ending of ANE in their name, are hydrocarbons where only single bonds are present. Okay, so we're always going to have single bonds to any hydrogens that are present in a molecule, but we can have double bonds or triple bonds to one carbon to another. So in things like alkenes, molecules whose names are end in ENE to designate that that's the family that they belong to in the hydrocarbon list, these are organic compounds that have one or more double bonds. So again, those double bonds have to happen in the structure within the carbon-to-carbon network. Notice too that when we hook together one carbon to another, that's going to take part in the count of bonds that we have attached to that particular carbon. We are never going to run into a situation here where we have lone pair electrons on carbon. Instead, all the hydrogens in an organic compound are going to basically cap off any of the extra places that aren't a connection between one carbon and another, or later on between a carbon and a different atom. So we can kind of think of this alkene, which is called ethene, as a carbon double bonded to a carbon. So two of the bonds are covered for each of these carbons, and then we just have to cap off the other two possible bonds with hydrogens on each carbon. Now, alkynes, designated with the ending YNE, are referring to triple bonded carbon-to-carbon bonds present in a molecule. So now here, each of the carbons in ethine are, and don't worry, we'll get into how to name these things later, so I'm just throwing the names out there for now. But each of the carbons here has 3 bonds already attached to it, so when we cap off the remaining possible bonds of the 4 with hydrogen, we end up with just a single hydrogen on each molecule of ethine, or on each carbon atom of this molecule of ethine. Now, aromatic groups named so because they tend to have a very distinctive smell. A lot of the spices and particular scents in products that you can smell and smell strongly are aromatic compounds, meaning that we have carbons connected, but in such a way that, this is going to be a very good ring, I'm sorry. Carbon, 2, 3, 4, 5, 6, and then connected back in on itself. Carbons connected in a ring structure. And this can have double bonds, or it can have single bonds, or some combination thereof. But aromatic is specifically referring to 6-membered ring molecules of carbon. So let's start talking about alkanes first. Now, when we have a chemical formula, just the simplest ratio of carbon to hydrogens, we're always going to have this general formula that we can use to recognize if this is an alkane, meaning a carbon containing organic compound with only single bonds. And what that is the CnH2n plus 2 idea, meaning that if I have one carbon, meaning n equals to 1, I will have 2 times 1, that's 2n, plus 2, that's the plus 2 in this formula, or 4 hydrogens attached to it. And then if we come up with the Lewis dot structure, we get this. Or the 3-dimensional structure, we get this. Now for the next most complicated version, C2, we can calculate out what we'd expect the alkane version of 2 carbons connected to each other, meaning the single bond only version, by just looking at that formula again. So n will equal 2. So the number of hydrogens is 2 times n, which is 2, plus 2, or 4 plus 2 is 6. That means we have H6. And if we draw out the Lewis structure of that, a carbon single bonded to a carbon, remember, hydrogens can't go in the center of a molecule, only the other atoms can. In this case, it's the 2 carbons. Those 2 carbons are connected, meaning one bond is taken up out of the possible 4 for each carbon. Meaning to cap off these carbons, we're going to need 3 hydrogens apiece. And now everything has an octet. So this 6 makes sense with single bonded carbon-to-carbon bonds. So each of these molecules is going to still obey the Lewis dot structure formulation. So we're still going to have octets, and we're still going to have 2 electrons for each hydrogen. Some larger alkanes, butane, the fuel for butane lighters. This is C4, H, let's see, 6, 2n, so 8 plus 2, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Hexane, which has 6 carbons, so C6, and then H, 2 times 6, which is 12 plus 2, 14. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14. Yep, 14. There we go. So you can see how this formula CnH2n plus 2 works, and you use it in two ways. One, to figure out how many hydrogens there are going to be for a certain number of carbons, and two, if I give you a molecule's chemical formula, like C4H10, if it has this CnH2n plus 2 ratio, then it will be only single bonds in that carbon, and you know it's an alkane, and you'll name it as such. Okay, so, just quick side note here, the polarity of hydrocarbons, we have so much symmetry for these structures that even though individual carbon to hydrogen bonds can be a little bit polar, they're mostly nonpolar anyway because they're so close to the electronegativity of each other. But even the slight polarity we have is symmetrically arranged around those carbons anyway. So we're going to end up with a predominantly non-polar molecule. So all of these hydrocarbons that we're about to talk about, the alkanes, the alkenes, the alkynes, and all kinds of alkenes, all of those things, those are going to be non-polar molecules, meaning that they're not going to mix with polar molecules. So for instance, water and all of these alkanes and alkenes and alkynes do not mix. They do not dissolve in each other. They'll actually form two layers just like oil and water. Oil, by the way, is a organic molecule, but oil and water form two separate layers. So will all of these organic substances we're about to talk about. So now these structural formulas start getting pretty nasty as we get to larger and larger and larger connections of carbons, and we can get to some really long molecules pretty quickly. So we're going to want to have a couple of types of formulas, and one of them is referred to as the condensed structural formula. And so the condensed structural formula just means that we're going to take the lines out and instead arrange these in units corresponding to the carbons. And what's immediately attached to the carbons before it goes on and attaches to another carbon in the series. So here we have a CH3 group, 1, 2, 3, attached to a CH2 group, CH2, and another one, and then a CH3 at the end. So this molecular formula is a condensed structure of this Lewis dot structure's description of the molecule that we refer to as pentane. Okay, so this is just an easier way to write this. You also might see just kind of a skeletal structure where all we show are the carbons, because we know hydrogen is going to cap off any available extra bonds, so we can really just kind of stick to the basics of what's connected and how many carbons are there and in what manner by showing just the carbons as well. And we'll refer to this in this class as kind of the skeleton structure of the molecule. There's actually one more method of naming these things, or drawing the structures, and that's referred to as a stick structure. And with that, we write sticks that bend, and at each point and at each vertex, we have a carbon present. That's what this designates. So we bend to show carbons, and again, the hydrogens are just assumed to be there. And this stick structure starts getting really helpful and effective when we have lots of branches and long chains and even more branches. It starts getting a lot easier to visualize and keep track of with a very condensed, just kind of stick orientation of the molecule. When we actually look at the lab where we construct little models out of wood sticks and little wooden spheres, you'll see as well that this actually mirrors pretty well the three-dimensional shape of these types of molecules. So it's helpful not only to say there's 1 carbon, 2, 3, 4, 5. 5 carbons here, counting the points and the bends. This is also helpful in terms of the three-dimensional structure being better represented. So if we look at propane, for instance, propane can be drawn out in a full Lewis structure this way. It has 3 carbons and 8 hydrogen. We can draw the condensed structure. We can actually draw a three-dimensional structure. We can draw a stick structure, 1 carbon, 2 carbons, 3. Right? And we can draw the skeleton structure. All 4 or 5 of these different representations are useful for different things. And if I ask you about a structure and want you to draw it, for instance, you can use any of these that you're comfortable with and comfortable drawing, unless I ask specifically for a condensed or a stick or a skeletal version of that particular molecule's connectivity. Alright, so we have this kind of sequential buildup of carbons. And we can just keep going with more carbons and more in a straight chain. And we have all of these names. The basics of these names, methane, ethane, propane, butane, the ANE is just referring to this being an alkane, meaning all single bonds. The meth, eth, prop, but, and even pent, hex, hept, oct, that's actually another Greek naming system, kind of like di, tri, tetra, penta, dealing just purely with the number that corresponds with the carbons present in that molecule. So we can look at the base names of 1 through 10 carbons just purely as the initial kind of, not quite a prefix, but it's close, that represents the number of carbons present. So 1 carbon, for instance, meaning CH4, is an organic hydrocarbon. It is an alkane because it's all single bonds. It has 1 carbon. So we name this meth, A-N-E, ane, methane. If we want to look at one of the main components of gasoline, for instance, and we can draw out the skeletal structure of this to save us writing all these crazy hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons connected to each other, all single bonds. We're not going to have double bonds or triple bonds to a hydrogen, right? So if we see all the bonds to the carbons and they're single, we know it's an alkane. So we'll have an A-N-E ending. We look up 8 and we memorize this chart and see that 8 refers to oct. So this molecule is octane. We've all heard of the octane content of fuels. We're referring to a measurement of these type of molecules in comparison to these type of molecules. So let's try this out. What are the straight-chained alkanes and the condensed formulas? Molecular, structural, and condensed formulas for the straight-chained alkanes with 7 and 8 carbons, and then name them. So pause and try this. Okay, so how does this work? So if we have C7, we can write the molecular formula. C7, so 7 times 2 is 14, plus 2 more is 16. So this molecule's chemical or molecular formula is C7H16. The structural formula is that whole Lewis dot structure. That's 7 carbons, so we have to draw it all out for the full structural formula. So we fill up to make sure everything has 4 bonds. And then we just write in some hydrogens to cap all of those off. Takes a while, but we can do it. Set. And so that's the full structural formula for this particular C7H16 molecule. So the condensed structure would be CH3, that's this cap on the end, then CH2, that's this guy, another CH2, that's this one, and another one, and another one, and another one, and so on. 1, 2, 3, 4, 5, 6, and then the last seventh one on the end. Nope, no. Erase. I don't know why it's flashing back to the previous screen there. The final one on this set is a CH3. So there's our condensed formula for C7H16. Okay? So the name of this, it's an alkane because it's the 2n plus 2 number of hydrogens, and because it said so, right? So we're going to end the name with ANE. 7, if we refer back to our chart, is hept. So this is heptane. Excellent. Alright, so the main thing about alkanes, or their main use, except as precursors in reactions to making more complicated molecules, is that alkanes are used a lot for fuels. So the type of fuel basically is going to depend on how long a carbon chain length we have. From 1 to 4, we're looking at natural gas like methane. Propane is used as a heating gas. Butane is used as an igniter gas for lighters and that sort of thing. C5 to C12, with octane being the most noteworthy known one of that set. These are things like gasoline. Slightly larger versions. These are jet fuels. Then we have central heating fuel oils. If you work off of an oil heated furnace, you're going to be looking at carbon alkane compounds with 18 to 20 carbons in them. Engine oil usually ends up at 20 or 30. So they have 5W20, 5W30. Guess what those 20s and 30s refer to. Ship fuel for the kind of thick oil that large ships use. C30 to C40 variety. And then once you get to things like C40, C50, these actually are less fuels and more waxy type substances, such as paraffin, which is used kind of a easily bendable, waxy films. A lot of times used to cover things, a lot like plastic wrap is. Petroleum jelly is a version of C40 to C50 carbon. And anything bigger than that, the only real use that we have for those, other than precursors to other things, or breaking them into smaller pieces to use for other fuels, are things like tars that are used in asphalt and road surfacing. Okay, so when you talk about saturation, saturated hydrocarbons, and even saturated oils, which we'll talk about later in the course, when we're talking about saturation, what we're talking about is that every available bond is being used up. If it's not a single bond carbon, then it's a hydrogen bond instead. And when we get to alkenes and alkynes, they're referred to as unsaturated, meaning that they have some other bonds besides going to hydrogen and single bonds to carbon present. So that means that we have double bonds present perhaps, so one of these two bonds is not a single bond to carbon, so it's kind of an extra one that is not going now to hydrogen atoms. So that lack of a full amount of hydrogen atoms spread across a molecule, that's what we mean if we talk about an unsaturated molecule. So the alkenes now. Alkenes, or ENE ending, is designating that these have at least one, if not more, double bonds. This actually makes them a lot more reactive because this bond wants to break, so it'll have only a single bond, and then the bond that breaks will reform with other molecules and other atoms to form a new molecule. Now these are named just the same way as we did the alkanes. The only difference is we change the ending. Instead of ANE, it's ENE. So if we have 3 carbons, for instance, we would just say, alright, it's a double bond there, so I'm going to end this name with ene. 3 carbons is prop, so this is propene. Pretty straightforward. Okay, so let's look at 1-hexene. Okay, so hexene means 6 carbons. And the 1 actually refers to as if we number these carbons, starting from one side and going to the other, that the double bond that the ene refers to is going to occur with a starting point of the first carbon. So 1-hexene looks like this. If we wanted to say 2-hexene, then that means that we're actually referring to this molecule, which we're showing in the skeletal formula. And so here, the carbon that the double bond starts on can be labeled as the second carbon from an edge. Now, be careful, because when we name these things, we look for whatever the closest edge is to the molecule. So if we had this molecule, for instance, it's still a hexene, but because the double bond is closer to the other side, we'll actually start numbering the carbons from that side so that we can minimize the numbers in the name. And so always be looking for what side can I start on to minimize any numbers I use in the name of the molecule. And so this is just another example of 1-hexene. And so here we have a number of structures, and we can do the same thing with condensed structures. The only difference for a condensed structure is, in order to show that there is a double bond, we usually actually write in the double bond, the double lines wherever it occurs, although you could technically tell where it occurs by the fact that we have fewer hydrogens than the corresponding alkane at that particular juncture. But this just shows it in a more clear fashion. And then again, we're just up in the number of carbons, prop, bute, pent, etc. Now, alkynes have double bonds, not double bonds, triple bonds, and we don't usually see these sort of things just floating around in nature. One exception is a fuel that we use for welding torches, ethine. The common name for ethine is acetylene. So ethine is actually 2 eth groups. All right, so this is an eth, and on the other side we have another eth attached by a triple bond. Okay, so this gives us, I'm sorry, this is not ethylene. This gives us 4 carbons altogether. 1, 2, 3, 4. And so 4 carbons, or these 2 eth groups attached to each other, for a total of 4 altogether, is going to give us bute for 4 carbons, and the YNE ending that we said way at the beginning designates a triple bond is present. Ethylene, instead, skipped ahead a little bit there, sorry, 2 carbons. So ethine would look like this. Okay. If there's more than one possible place, we don't have to name ethine 1-ethine, because there really isn't any other place to put a triple bond in this molecule other than between the only 2 carbons present. So we don't need to number it unless there's 2 possibilities. 2-butene, for instance, looks like this, with the second carbon being the starting point for the triple bond. We could also have 1-ethine, which would have a skeletal structure that looks like this. And so here's another table showing more ethines, more things of that nature. We forgot to go over this, but we'll go over this right now. The formula is no longer n plus 2, 2n plus 2. So let's look at what the new formula is for alkenes and alkynes. If we want to be able to use this so that if we get just a molecular formula and not a name, we can recognize whether it's an alkane, an alkene, or an alkyne simply by the ratio of carbons to hydrogen. So the formula for alkenes is, and you can think of this, we'll show why this makes sense in a second, is just for every carbon, I'll have twice as many hydrogen. Now remember, all of these middle carbons, any ones that don't appear right at the end, are all going to have 2 hydrogens apiece. So that double number. If it's an alkane, I would have 2 additional. That's the +2 that comes in for alkanes. It's the ones on the very end caps of the molecule. For an alkene, where we have a double bond, we're going to have to get rid of those electrons. So that means we're also getting rid of a hydrogen here. And in order to have this group be alright, because now it has 5 bonds, we have to get rid of a second hydrogen as well. So the +2 goes away because the double bond takes up the bond for 2 carbons that would otherwise have gone to hydrogen. The same reasoning for alkynes, things with triple bonds, leads us to the correct ratio of CnH2n minus 2. Because now, if we introduce a triple bond to this molecule, watch what happens with the carbons. We already went from CnHn plus 2 to CnH2n for the alkenes. But now, if we put another bond in here to make this a triple bond, we have to again get rid of some hydrogens in order to have only 4 bonds still around that carbon. Okay, so alkenes, CnH2n, alkynes, CnH2n minus 2. So whenever we get a formula, C4H8, we can look at that and immediately say, alright, hydrogen is twice as much as carbon. This must be an alkene. Or we get something like C5H8. This is twice as much hydrogen as carbon, but 2 less than twice as much. So that is a alkyne. Okay. So back to this. These are the alkynes. C4H6, so 8 minus 2, 10 minus 2, etc. gives us these structural formulas and these names. Okay, so what's 1-hexyne? The structural formula, that means the full Lewis dot structure. So pause it, give it a try, come back. Alright, you're back. So I would draw the skeletal structure first, with single bonds. So 6, that's what hex refers to. 6 carbons. Now we need a triple bond. The 1 tells us that the triple bond is right here on the first carbon. And now we fill in extra bonds with hydrogen. That 1 hydrogen there gives me the 4 total bonds I need for this first carbon. The second carbon actually already has all of its bonds, the triple to carbon and the single to the other carbon. And now from here on out, we're going to have to fill in the other 2 bonds with hydrogen. And then when I get to the end, I'm going to have to fill up 3 because there's going to be that kind of end cap hydrogen as well. So altogether, the still fits are twice as many as carbon, which is 12, minus 2, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know this is the proper structure for 1-hexyne. Now, this is where it gets exciting. Now we start branching. Now, there's a couple of ways to name the branches. And the more common version that we see is if it branches, we still just count up all the carbons present, even though it's branching in not one nice linear straight line chain. and we just call it iso, whatever the heck it was originally. So if it's butane, and we want to say that it's not branched at all, we can just say butane, or we can be really specific about it and say N-butane, meaning no branches at all, and it'll look like this. If instead we have 3 carbons with the 4th carbon branching off the middle, this is still 1, 2, 3, 4 carbons, but it's now, we refer to it as isobutane, meaning an isomer. It's still butane, but it's slightly different. Now, isomers are still different in their properties. This molecule is actually more compact than this molecule up here, which will give it a slightly different set of properties in terms of its very negligible but still existent tiny bit of polarity for a mostly nonpolar molecule. Something to realize, these are both butane. 4 carbons. 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Branch, 1, 2, 3, 4 carbons. 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. You cannot tell from the simple molecular formula what isomer is present. So what we're just seeing here is, if I do not learn to use structural formulas and read structural formulas, I cannot tell the difference between 2 molecules that have the same molecular formula, in terms of this molecular ratio of carbons to hydrogens, but will end up having actually different properties in the end because of their connectivity, how the carbons are connected one to another. Okay. So now you can also, besides branches, we also talked about earlier, so why am I reintroducing it again? I just want to show you that we can call these isomers of each other just by the difference in position of a triple bond. So while we'll have 1, 2, 3, 4, 5, so pentyne, and on the first carbon, so this is considered the normal or the standard pentyne. On the second carbon, we can either call it 2-pentyne, or we can collectively refer to those that have other placement besides the first positions as isopentynes. Alright, so we're going to start naming branches a little bit more specifically, because as we get into bigger molecules, we're not just going to have one other possibility. We're going to have lots of other possibilities for how to connect things. So we want to be able to distinguish between them because they'll have different properties, even though their chemical formulas might be identical. So what we'll do is introduce the concept now of an alkyl group. An alkyl is just a branch off of the main chain. Okay, so right here, we're going to say this nice group of 5 carbons in a row is the main chain. Okay. An alkyl group might be a carbon with, this is the skeletal structure, so keep in mind there's hydrogens around all of these. But this branch off of the second carbon to another carbon is the alkyl group, or one of the alkyl groups. We can have more than one of these on this particular 5-carbon main chain. Okay, so when we name this alkyl group, we still use the metheth, prop, but, etc. system, but we'll change the ending to YL to indicate that this is actually a branch and not the main chain of the molecule. So this particular, if it's 1 carbon side chain, means that what we have here is a methyl group attached to the 5-carbon main chain. If I had put, for instance, 2 carbons off of this main chain, this is now 2-carbon side chain, and we would refer to this as eth for 2 carbons, and an ethyl branch off of the main chain. Now we're going to get into more details how to name this in just a second here. So naming these things is done by naming first the longest continuous carbon chain. Now don't think that's just the one that I've drawn straight across the page. We can have chains that go in different directions. Okay? And that's still 1, 2, 3, 4, 5, 6, 7. That's still a 7 continuous one after another carbons in a chain. So we would still call this a heptane molecule. If I start adding branches, I have to keep in mind that I still need to locate whatever the continuous straight chain is in this molecule in order to name this. So the base main chain that I name as part of the molecule is still going to be 7 carbons, even if it looks like I have this straight chain from left to right without deviating from my straight path here. It looks like it could be 5, but 5 isn't the longest chain, 7 is. Okay, so here's another one to kind of try this idea. Okay, so what's the longest chain of carbons here that's present? And here we'll even make it a little bit more complicated. Ooh, fun. Okay, so we can kind of think, let's see, 1, 2, 3, 4, 5, 6, 7 maybe, or 1, 2, 3, 4, 5, 6. Okay, so that's not the longest chain. Maybe 1, 2, 3, 4, 5, 6, 7, 8. Ah, there it is. So when I name this, I'm actually going to name this as something with a methyl group and an ethyl group off of an 8-membered continuous main chain of carbons. Okay, so locate the main chain. That's the first step. Then determine what branches are off of that main chain. Those are the substituents, the YL alkyl groups. Then you're going to number the base chain, beginning with the end closest to the first branch. And so here, let's see, 1, 2, 3, 4, 5 gets us to where the branches are if we start from that side. Yet 1, 2, 3, 4 gets there sooner if we start from this side. So 1, 2, 3, 4, 5, 6, 7, 8. That's our numbering system, the one that gives us the shortest path to the first branch that occurs in that molecule. So this numbering system, starting from the top and working our way down, gives us 4 as the first substituted position. Okay, so now that we have that, we're going to number the substituent names and put a dash in. Okay? We're going to name the substituent with the base name of the compound. So what we're going to have here is a 4-ethyl. So we'll say 4, then a dash, then ethyl. We're going to put another dash because we have another substituent. And that's at the 4 carbon that it branches off of. So we'll say 4 again. And this is a methyl substituent, methyl branch. So 4-ethyl right here. 4-methyl right there. Dash again to say that we're done naming that side chain. And then we have no more side chains, so we go ahead and name the base longest chain. And that's an octane. So octane. So this compound is 4-ethyl 4-methyl octane. These names get ugly fast. But all it really is this is kind of a step-by-step set of instructions to write out the formula or the skeletal formula, or any formula for that matter, of the actual connectivity of the molecule. And so let's try one the other way. How about a 2-methyl? I don't know why I put a comma there. 2-methyl 4-propyl decene. Okay, So 2-methyl 4-propyl decane. So when we want to write this out, make it easier on yourself. Give it a straight chain for the main chain of the compound. Okay? So decane is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Make it easier on yourself again. Just start numbering from left to right. 4, 5, 6, 7, 8, 9, 10. Okay. So 2-methyl means at the 2 position, we put a single carbon branch for meth. At the 4th position, we put a propyl. So that's prop is 4. So if we go a 4-carbon branch, 1, 2, 3, 4. We could have drawn it straight down if we had room, or we can make it bendy. It doesn't matter. The bendiness and the directionality doesn't matter for these. In reality, all these single bonds are floppy and kind of floating around and wiggling and doing that kind of stuff anyway. The important thing is to show what's connected to what and how long those connections run. And so the 4-propyl gives us 4 carbons because it's prop at the 4th position because we have a 4 here. And this is it. That's our molecule. So it looks pretty nasty, but in reality, it's just a step-by-step set of instructions on how to name these things. Okay? So let's name this one. Longest chain, you can pause it of course, but longest chain, left to right, straight across here. There it is. We're going to start numbering from the side that reaches a branching point first. So here's our branch. It's faster to get there if we start from the left-hand side. Okay, so we have a total of 6 carbons. So that means it's a hex. This is the base molecule. It's all single bonds. So that's a hexane. And the substituent is off the 3rd group. So we call it 3. The substituent is a methyl group because it has only 1 carbon. Connect things with dashes, and we're done. 3-methylhexane. Yep. And here's where we spell it out from start to finish. Alright, when there's 2 or more substituents, we have these naming rules. And in all reality, if you don't follow this perfectly, people will still be able to figure out what in the world you're talking about. But when you want to be chemically, grammatically correct, for instance, we have some rules on how to name these things. The lowest possible numbering system, we already talked about. If there's more than one substituent present, like an ethyl or a methyl and that sort of thing, don't name it starting the lower number first. Start it with the alphabetical one first. Okay? So if we have, for instance, there we go. If we have this heptane base chain, so that's the base molecule, and a branch first reached at the 2nd carbon, so we start numbering it from the left to the right. The longer path is to keep going to the right here, so we'll keep going 5, 6, 7. That's how we knew it was heptane instead of hexane if we would have turned left for the main chain. It's a 2-methyl and a 4-ethyl. When we number it, it was numbered by whatever hits the branch first. When we write the name out, ethyl comes first because it's alphabetical. So we'll actually say 4-ethyl, 2-methyl. And another dash that we're not going to really be able to see, but there's a dash right there. Sorry. Yeah. So 4-ethyl, 2-methyl. We do it this way because we're not paying attention to the number to place what goes first. We're paying attention to the alphabetical order of the substituent. Now, if we have identical substituents, like say we have this hexane. I have a methyl here and a methyl there. We're going to say number it from here. 1, 2, 3, 4, 5, 6. It's a hexane. There are 2 methyls, so we're going to use the prefix to say there's 2 of them. We still have to say where they're at, so we're going to say 2, comma, 3 to say that what we're about to name occurs at the second and at the third carbon, dash, dimethyl, dash, hexane. Okay? So that's how we'd name this molecule, 2, 3, because the branches occur on the second and third carbons, di, because there's 2 of these methyl groups, methyl, because the groups each have 1 carbon, and hexane, because there's 6 carbons in a row. Let's look at another example. Very similar. Okay, so we can say carbon here, carbon here. It looks real similar to what we did last time, except I'm going to branch it the other way off this same second carbon. So we know it's going to be a hexane. We know there's 3 methyls, so it will be a trimethyl hexane. We just have to do the numbers. We want to say that these 3 methyls are there. If we just say 2, 3, because there's branching at the second and the third carbon, we know that there's at least 1 on the second and 1 on the third, but that doesn't tell us well enough where the third methyl is. So when we have more than 1 on that particular branch, we put the number in twice. So 2, 2, 3 means 1 methyl on the 2, another methyl on the second carbon, and a methyl on the third carbon to make a trimethyl hexane. We're going to practice this in class, don't worry. Okay, so let's name this guy. Let's see, longest group, 1, 2, 3, 4, 5. We go to 6, 7, or 6, 7. It doesn't really matter here, so let's just make it easy on ourselves and go straight across. To number it, 4, 5. Yeah, you can't name anything until you figure out what your longest chain is. This is our longest continuous chain. Alright, we knew to name it this way because we get to a branch at the second carbon going from left to right. If we would have gone from right to left, it would have been the third carbon that had the first branch. So the lowest number possible will be starting from the left and going right. Alright, so we have a 1, 2, 3, 4, 5, 6, 7. So we have a 7 carbon backbone. That's hept. How many bonds? All single bonds, so heptane. Now we start listing substituents. We have a dimethyl set here and a ethyl set here. So it's going to be a 5-ethyl and a 2, 2 dimethyl. Now we just have to figure out what order to put these in. E comes before M, and we don't look at the prefix. E comes before M, so we put 5-ethyl, 2, 3 dimethyl. Would people have still known what the heck you were talking about if you put 2, 3 dimethyl, 5-ethyl heptane? Yeah, sure. But we're trying to go most grammatically correct chemistry-wise, so this is how we name it. Alright, so branching when you have double bonds doesn't really change anything. The only thing it changes is we give priority in numbering to the multiple bond. So 1, 2, 3, 4, because the double bond starts on the first carbon here. We start on this side because we reach the double bond sooner than if we went from left to right. That would be 1, 2, 3 pentene. If we start from the right and go left, it's 2 pentene. Okay, so 2 pentene, ene because it's a double bond, 2 because it starts on the second carbon, 4 methyl because we on the fourth carbon have a 1 carbon meth group that is a substituent. And the rest just flows the same way. Now, the only real addition we have to this is that we can start adding non-carbon compounds to these groups and end up with different properties. First one we're going to look at is an alcohol group. And that group is a OH compound. Now this is not hydroxide ion. Right? It's actually a covalently bonded oxygen and hydrogen to this ethane group that we had before. So we do this, we actually change the ending a little bit to represent whatever specific functional group we're attaching this to, and that way people will know what it is we're talking about for this particular molecule. Because these functional groups are something we can talk about based off of just what group is different than just a regular alkane, alkene, or alkyne, we start having a generic symbolism where we say R, which is the whatever the heck the hydrocarbon is, the alkane, kene, or alkyne. We can just represent that whole chunk as R. And then whatever the functional group is, we'll write actually out the molecules or the elements connected in the correct way to show the actual non-alkane portion of the molecule. So we can say generically an alcohol is any ROH molecule, meaning any alkane, alkene, or alkyne connected with an OH somewhere on that structure. And so classifying these things this way helps us to really kind of organize compounds based on their properties. Alcohols, regardless of what the R group is, will have a certain type of property that's common to alcohol molecules. So these physical and chemical properties kind of center around the functionalities that are on that molecule. So here's a whole bunch of different functionalities. You can have chlorinated hydrocarbons. That just means there's at least one, if not more, chlorines attached to that molecule. To name that, you just call it chloro, and mono, di, tri, however many there are. In this case, it's di. And methane, meaning that it's attached to what used to be, before I put the chlorines on it, a methane group. Okay? So alcohols, we just said, are ROH. An example of this would be ethyl alcohol. So we can either name this by saying that this is an ethyl group in a side chain off of the alcohol, or we can call it eth and change the ending to OL, indicating an alcohol. Aldehydes have a structure where you have something alkanish and you attach it to a carbon double bonded to an oxygen. The Lewis structure would actually show some lone pair electrons up there and attach then to a hydrogen. So this caps off the end somewhere of a molecule. When we do that, we can either call it ethyl aldehyde, like we did ethyl alcohol here if we want to call the carbons present. Now notice we're naming and numbering the carbon that's also present in the aldehyde functional group. So 2 carbons here, ethyl, and we can name that then with an ending change to AL. So ethanal is the ethane, 2 carbons, but with a double bond oxygen, single bond hydrogen grouping. Okay. Acetaldehyde is whenever you run into these 2 carbon organic molecules, acetyl is a common or older naming system, so you'll have to kind of keep that in mind. The more scientific way to say this way would be ethyl aldehyde. So ketones and acetone is an example of that, is where you have one type of alkane, a carbon double bonded to an oxygen, and then that links together to a second alkane, which can be the same or different than the first one, and that bridging carbonyl, C double bond to an oxygen group, is what makes this a ketone type of molecule. That's the name of the functional group. So here's an example where the bridging carbon is between two carbons. So there's 3 carbons altogether, so this would be a prop group. And we don't typically call ketones propyl ketone or methyl ketone, although you could see that periodically. What we do though, is change the ending. Instead of ANE, we change it to unknown, ANONE. That's not very clear. ANONE. So prop, meaning 3 carbons all together on this chain. It's a bridging C double bond to oxygen, so that's a ketone. So propanone is the name of that molecule. And again, these acetyl groups, talking about how I have 1 acetyl, 2 acetyls, that's a more common naming system method in terms of kind of like how ferric and ferrous are the iron 3 and iron 2 ions, but the ferric and ferrous is kind of the older, generally used in an unofficial capacity sort of name. Acetone is the general unofficial name for this particular molecule as well. Now, carboxylic acids have a carbon attached to double bonded to an oxygen, single bonded to an oxygen to a hydrogen. So this is what our group looks like as a Lewis dot structure, and then attached to something else, some other alkane. And here again, we're going to name this, including the carbon in the functional group, and this would be ethanoic acid if we named it officially. Ethanoic acid. So to name an acid, we're using acid at the end, just like we do with all acid, but we're going to change the ending to anoic. And use the prefix of meth, eth, prop, but, etc. And the common name for the 2 carbon groups are acetyl, so this would be acetic acid as a common name that you should know. This is the acid that's present in vinegar. Now we have esters and ethers. These are very similar to each other in terms of their properties, but they have a slight difference. Here, instead of bridging with a carbonyl, a C double bond to oxygen, we bridge and have an additional oxygen that's attached. Okay? And so we double bond to oxygen, single bond to oxygen to carbon. Or for an ether, which are extremely reactive, flammable, combustible substances, ethers just have a bridging oxygen between 2 possibly different alkene or alkyne groups. So for this, 2 examples that we have are methyl acetate. Okay, so we have a methyl group and a methyl group on either side. Okay, so we call this methyl to indicate what's on each side. If there was a methyl and an ethyl, we'd call it methyl ethyl acetate. But moving on from there, I'm not going to make you get too crazy with naming these functional groups, by the way. Alcohols um, and amines are ones that I will definitely make you name and come up with the structures for. The rest, I'll let you use a chart for and expect you to be able to figure out what they are based off of looking it up on a table or a chart. Alcohols and amines come up often enough, and actually carboxylic acids as well, come up often enough in the rest of the chapters that those I want you to know by sight without having to look at a table if at all possible. So anyway, esters, we're looking at an ending of ATE. So if you see an ATE ending in an organic molecule, that means it's this carbon double bond oxygen, single bond oxygen, off to another type of alkane. Esters are the bridging ones. Those are just referred, ethers, I'm sorry. Ethers are just referred to as ethers. So we just have the word ether at the end. We don't have any ending suffix changes for these. And we just name whatever it is that's on either side of that bridge. So we can have two methyls, and then it's dimethyl ether. We could have a methyl and an ethyl, and that would be then methyl-ethyl ether. Or you have two ethyls, that would be diethyl ether. So it's just all you're naming is what's on either side of the oxygen, and then say ether to say that whatever I just named is bridged by an oxygen. The last functional group we're going to bother you with, the amines. Amines just means there's a nitrogen in there somewhere. Now remember that nitrogens have 5 valence electrons, so when they form Lewis dot structures, we're going to have a double electron or electron lone pair here in the nitrogen. So nitrogen's only going to form 3 bonds, and those can be to hydrogen, or those can be to different alkanes, or some combination thereof. The way we name this is we name it with the word amine, and then we just name the other chain as if it was an alkyl substituent. So if there's just one, like this ethyl group for instance, before the nitrogen, we can call this ethylamine. And if there were two, we would call two ethyls attached to the nitrogen, we call it diethylamine, etc. Okay, so name this guy. Well, we have 1, 2, 3, 4 carbons, including the functional group. The functional group is a carboxylic acid group. So this is a carboxylic acid. So we can go with either the very systematic way, 4 carbons would be prop, and then anoic designates it's an acid. And as with all acids, we're extra careful to put the word acid at the end so people know what this is. So this is propanoic acid. All right, so chlorinated hydrocarbons, these are pesticides, refrigerants, that sort of things. Those are just substituted in chlorine somewhere in the structure. So if you see that, we're going to refer to that as a chlorinated hydrocarbon. We're not going to get into how to name this guy. So don't worry. All I would want you to know from a molecule structure like this is these are chlorinated, a version of chlorinated compounds. Now the reason people do this is it usually makes them less reactive than just alkanes or alkenes or alkynes. Those chlorines prevent oxygen from getting in and reacting with this carbon in a burning combustion type process. So that makes them more stable than other molecules, which is why we use them in things like refrigerants that we don't want to have burn up or oxidize in any particular way. Now chlorofluorocarbons are even more stable, and that's where we put fluorines and chlorines into a molecule, and those are incredibly stable. Unfortunately, though, they're so stable that they survive without breaking down until they reach the upper atmosphere, where you have some really high energy sunlight that gets through at that level and ends up giving us a broken down product. And that broken down product of chlorofluorocarbons is actually one of the main causes for destroying ozone, ozone being an O3 molecule. And that ozone is there naturally in the atmosphere to absorb ultraviolet light that would otherwise cause sunburns and skin cancer and that sort of thing. Because of that, we've pretty much banned most of the chlorofluorocarbons and instead have used other more saturated molecules that decay faster, meaning in reality they're not going to last as long in air conditioning systems where these sort of things are usually found, but it's also going to not destroy the ozone layer and let us all die from sunburn. So there's some trade-offs. Okay, so alcohols, actually I'm just kind of rehashing myself here a little bit. The OH group makes this polar, and this is pretty highly polar. Ethanol is one really easy to remember example. This is the drinking type of alcohol. The other types of alcohols are poisonous, but ethanol our body can process, at least in low doses. The increased force makes these molecules liquids. This polarity or attraction of one ethanol to another, because of the polarity of this group, actually makes these things stick together as molecules better than an alkane would. Right, so the original alkane without the functional group is just ethane. Ethane's a gas at room temperature. Because it's nonpolar, these molecules aren't attracted to another ethane or another ethane next to it. And since they're not attracted to each other, they can float away from each other fairly easily and end up keeping this as a gas state molecule. Now the polar alcohol group, though, is enough stickiness, enough polarity, that one of them sticks to another and to another, and that keeps it as a liquid state instead of the molecules floating apart from each other like a gas. Okay, alcohols are made from sugars. Okay. This is one instance of a sugar. Sugars have the main formula of CnH2nON. Okay? And these are carbohydrates because basically what you have is carbons and waters in a way. In reality, these are actually a bunch of alcohols all attached to a long chain of carbons. We're not going to get into the structure here, but when this ferments, you have organisms that break these multiple alcohol groups apart, and we end up with smaller portions of this. So the C6H12 breaks into a couple of C2s, and the C2s keep their OH alcohol group, in this case ethanol, and we also get some carbon dioxide that's given off that kind of gets rid of the caps and the ends of the molecule. Now, ethanol acts as a central nervous system depressant. We all know there's health effects, liver damage, brain damage, drunk driving, etc., that can happen from ethanol consumption. But it's not directly poisonous unless you have a high enough dose of it. Isopropyl alcohol is an isopropyl group, meaning that the alcohol is not going to be at the end. It will actually show up here in the middle. And this isopropyl alcohol is rubbing alcohol. Very toxic. You can't actually drink that. You can rub it on your skin, that's fine. It evaporates quickly, although it starts as a liquid. And it works for wiping off grease and stuff like that. And actually, we use this as well for killing off microbes before you give people shots or put in IVs. Methanol, the simplest alcohol, is pretty toxic. It's much more toxic than ethanol. What you can do to clear this out of your system if people accidentally drink methanol, because it smells just like ethanol does, is you can actually flood your system with ethanol by drinking a lot of the drinking type of alcohol, and that will get rid of the liver's ability to catch and grab onto and try to process methanol and therefore kill your liver, Instead, your liver will be just tied up with ethanol, dealing with the ethanol in your bloodstream, and the methanol will just pass through and eventually be excreted. Now, aldehydes and ketones, right, we can recognize. Here's our ketone group. Here's another ketone group. And we can put it on these rings. We didn't get into what these rings are. They're phenols. They are carbons in a ring, and they have alternating single and double bonds. And there's some hydrogens attached to that as well, but that's the basic idea. Most of our scent molecules come from these ring structures, these phenyl groups. We're not going to get into how to name them, so don't worry about that. But this particular structure, for instance, cinnamaldehyde, that is what your nose detects when you smell the product cinnamon. Benzaldehyde, I believe, is almonds. It's the scent that you get from almonds, or artificial almond scent, almond extract kind of scent, can just be derived from taking this molecule alone instead of having to actually isolate an oil from the almonds themselves. So phenyl groups, circle groups usually are scent molecules. Exactly where a aldehyde group is in that affects exactly what the scent is for that molecule. So we went over this before. The simplest version, formaldehyde, forma. You can see this. It's kind of like ferric and ferrous. Forma means one carbon. So formic acid would be a one carbon acid. Formaldehyde is a one carbon aldehyde. I'm throwing a lot of these common names in here just so you're not thrown off if you see this. But the proper name for this, as we talked about before, is methanal. Methanal or formaldehyde is usually used for killing biological organisms. So, for instance, if you flood a dead body with formaldehyde or methanal, you will kill off all of the bacteria that it would otherwise process and eat through those dead cells and use them as food. So you can keep biological specimens from being decayed by bacteria by soaking it in formaldehyde. And so ketones basically impart the property of increased flammability and increased evaporation speed over that of an alcohol. We talked about how to name these already, and that acetone is the simplest version of this. And there's the structure. Carboxylic acids have a tart taste. They tend to be weak acids, so these are not the sort of things that dissolve your skin. Instead, they will just be acidic, so they can give you things like heartburn, but they're not going to burn a hole in your esophagus unless you're dealing with carboxylic acids from really hot peppers or things of that sort. So formic acid, the simplest one carbon one. This would be actually methanoic acid if it was named by the systematic rules. It's actually excreted by ants onto their shell, meaning that ants will taste tart if you eat them, and some people do. But methanoic acid is excreted onto the shells as an acid, which helps them to keep from being eaten by smaller predators and other insects. And we know how that group looks. It's a C double bonded to an O to an H. So here is the carboxylic acid group. Some things have multiple carboxylic acids. Citric acid, for instance. We're not going to get into how we try and even name this group by a systematic set of names, because that would just be getting way too complicated for this class. But do note that we can have mixed functional groups in things, and that will impart a whole set of properties that is unique to the molecule. So 3 carboxylic acids and 1 alcohol group, and we have citric acid, one responsible for the taste in oranges, lemons, limes, that sort of thing. Okay, esters also have a scent. Usually it's a nice scent. People refer to this as being a pleasant scent as opposed to a horribly bad chemical scent, although there is that side of these as well. Okay, so this is an ethyl. and butyl group for a ester functional group. So we would name this as ethyl butyrate. So an ethyl attached to a butyl, and then the ATE ending. So we're just adding that ATE ending. This ethyl butyrate is responsible for the scent that we detect as pineapple. And this is an ester. You see these a lot also in perfumes. If people want to smell nice, the fruity scent of perfumes are usually esters. Ethers, the most common diethyl ether, looks like this. The functional group is just a bridging oxygen. And we name these just by naming, like you said, the groups that are attached to that bridging oxygen. This is used as one of the earliest general anesthetics. It knocks people out, gets into your lungs and your bloodstream and causes unconsciousness. It can also depress your breathing, so it can kill you pretty quickly. Inhaling this, if you inhale too much, it'll just stop your heart from beating and your lungs from moving, and you'll die. So that's why you have to pay somebody $100,000 plus a year to sit there and hold the mask on you carefully and make sure you don't die during surgery. And then our last compound that we're going to talk about in more detail, amines. Dead things, bacterial byproducts, a lot of those sort of things are amine compounds. Decaying fish is the most common amines. That fishy, icky smell that you see is one of the main amines that people recognize on an easy basis. That general formula that you have nitrogen there. Putrescine is a common name for this diamine. 1, 2, 3, 4 carbons, so a propyl diamine group. You can't bridge very well. Well, I guess you can't bridge with nitrogen. I'm not going to say that. But again, I'm not going to get too crazy with the names of these substituent groups. I just want you to be able to recognize, this is an amine. So property-wise, this molecule is going to be stinky. It's an amine. Okay? So we talked here in this chapter about organic versus inorganic. Inorganics are ionic substances, which are salts and stuff like that. Organic, mostly carbon with other things attached to it. We talked about what hydrocarbons are. 3 main types of hydrocarbons and how to name them, including branches. And then we did a little survey of the functional groups, which I want you to be able to recognize. And during that, we talked a little bit about different uses and different ways you've seen examples of these things already. And that's chapter 6.